Hello, my fantastically wonderful children. You are at home right now for this fantastic snow day. I am so excited that we got a snow day. I am sure you are too. Today we're going to talk about the liquids and solids, and that means that we'll only have one section left to cover from chapter 12, which is phase diagrams. So I've decided that your quiz will still be tomorrow, starting with chapter 12 with the gases, moving through gas laws, and then intermolecular forces, and then also these liquids and solids. So phase diagrams and phase changes, we've talked about phase changes, but phase diagrams is something that will be new to us. So we'll talk about those on Friday, and then that way during OGT week, we can just do a series of labs and introduce mixtures and solutions with also doing just a series of labs, okay? So I'm going to go ahead and get started on these slides, and these slides are new, so I have them posted up along with this video. I'm also going to post up the slides for the phase changes and phase diagrams, just a part of the liquids and solids slideshow, so make sure that you bring that to class with you on Friday. And you do have your quiz tomorrow still, and I again will post some sample questions for just some practice for you so that we kind of have an idea of what I want you to know for tomorrow, okay? So first thing, we are going to first focus on liquids, and we know that liquid particles can flow to adjust to the shape of a container. So we know that liquids flow, and we know that they have a fixed volume, but they don't have a fixed shape, because they are able to flow. Now, I know that for gases, we talked about the kinetic molecular theory, and the kinetic molecular theory was developed to explain behavior of gases. However, the kinetic molecular theory can also apply to liquids and solids. The only difference between gases and liquids and solids when using that kinetic molecular theory is that for liquids and solids, we also have to consider or take into account the forces of attraction that are happening between particles of liquids and solids, as well as like their energy of motion, because we know that gases are able to move in such a different way that liquids and solids are. We also know that liquids and solids have more forces of attraction between those particles than gases do. So just keeping that in mind, okay? Now, I have on here, liquid particles can flow to adjust to the shape of a container, but the liquid cannot expand to fill its container. Why can't a liquid expand to fill a container? The biggest answer is that forces of attraction are keeping these molecules in a liquid very close together in kind of more of a fixed position. So it's not necessarily a fixed position, but because they're still able to flow and move around. But it's making those intermolecular attractions, those forces of attractions, are keeping the molecule so much closer that they're not able to fill up the entire container like a gas can. So intermolecular attractions, or forces of attraction, are the reason why there's a fixed volume, but there's not necessarily a fixed position or a fixed shape, okay? Now, in terms of liquids, liquids have a lot of characteristics about them. So density and being able to be compressed are a few different characteristics that we're going to talk about liquids. So liquids are much denser than gases, and that's because they have strong intermolecular forces holding those particles together. So since those intermolecular attractions or intermolecular forces are so much stronger in liquids than they are in gases, that's the reason why liquids are so much denser. Now, unlike gases, liquids are considered to be incompressible in lots and lots and lots of applications. However, we have been able to compress liquids to just very small amounts if we apply a lot of pressure. And again, that's pretty rare, because for the most part, liquids are considered to be incompressible. Now, another characteristic of a liquid would be fluidity. So fluidity here is the ability to flow and to diffuse. So liquids and gases are considered to be fluids. So a fluid is just something that has the ability to flow and something that also has the ability to diffuse. So liquids and gases are fluids, but solids aren't fluids. I put this picture up here because this would be an example of a liquid diffusing through another liquid. And we know that liquids would diffuse more slowly than gases at the same temperature, just because the intermolecular attractions are going to interfere with the flow. So since liquids have stronger intermolecular attractions holding those liquid particles together, then that's why they're not going to diffuse as quickly as a gas would. Now, another factor of a liquid, or another characteristic of a liquid, is a liquid's viscosity. Now, how I like to think about viscosity is like syrup or honey. And you know that if you have syrup that's in your fridge, then you try to pour that syrup out. It's super sticky, it's really slow, it's super hard to get out because it's viscous. If you place that syrup in the microwave and you microwave it and heat it up, you add some extra energy to it because of this heat, then it's not as viscous. It's more able to flow. So viscosity is just a measure of the resistance of a liquid to flow, and it's determined by a few different things. It's determined by the type of intermolecular forces, it's determined by the size and shape of the particles, and it's determined by temperature. So there are three major factors here that can determine viscosity of a liquid. So that's intermolecular forces, size and shape of the particles, and then also temperature. Okay, so continuing with our viscosity, the stronger the intermolecular forces are, the higher the viscosity. So think about that. If I have intermolecular attractions that are holding these particles closer together, then, and I have more of them, the stronger the intermolecular attractive forces, the higher the viscosity. So that means the stronger the hold on these particles being close together, the more viscous it's going to be. Now, this is an example. I have two molecules here of glycerol. So you have one up here, you have one right here. And this glycerol, this can show that when these molecules are close by one another, they're going to interact with each other, and they're interacting through those intermolecular forces. And specifically in glycerol's case, hydrogen bonding is what keeps glycerol so viscous. So here's my first molecule, and then I have my second molecule down here. If I look at this, the oxygen on this second molecule of glycerol has some type of hydrogen bond with the hydrogen on molecule number 1. So I can see that I have a hydrogen bond right here. Well, I have a hydrogen attached to this oxygen in molecule number 2, so that hydrogen is attracted to, through hydrogen bonding, the oxygen on molecule number 1. I see the same thing over here. This oxygen is attracted to the hydrogen of the other molecule, and this hydrogen on molecule number 2 is attracted to the oxygen on molecule number 1. So I see that I have hydrogen bonding that's keeping these attractive forces really strong between these two molecules. So that's what makes something viscous. And specifically in this case, let's say that I added another molecule down here. Let's say I added a third molecule. How many hydrogen bonds would be made if I had molecule 3 attached to molecule number 2? Well, if I can look up here, I have one hydrogen bond right here. I have a second one right here, third one, fourth one. So between these two molecules, I can have 4 hydrogen bonds. And so if I added a molecule down here, it would make another 4 hydrogen bonds. Okay, so that's the way that attractive forces can determine something's viscosity or a liquid's viscosity. we said that another factor that could determine the viscosity of a liquid is particle size and shape. So large molecules, very large molecules, can create a greater viscosity. And size and shape can also affect, we know that size and shape can affect viscosity, but most of that is because, think about the kinetic energy of a liquid or a gas or a solid. We know that kinetic energy is dependent on two factors, and that's mass and that's velocity. So if I have a huge, massive molecule, it's going to move pretty slow, right? Because it's big and it's massive, so it's going to have a pretty low speed. So if I have a really big, large mass, then they're not going to be able, on average, these large molecules will not be able to move as fast as a smaller molecule or a smaller particle, because a smaller mass could mean that I could have a higher speed or higher velocity. Now, long chains of molecules also can result in higher viscosity. And think about that. If larger molecules have a greater viscosity than really long chains of molecules, because if I have a long chain of something, that means that I'm going to have a pretty large mass. And typically we see that in everyday life with cooking oil or with motor oils. Now, temperature was that third factor that can determine a liquid's viscosity. Now, increasing the temperature will decrease viscosity. And that's because if I increase temperature, if I'm increasing the temperature of this liquid, then that means that the kinetic energy is increasing. That average kinetic energy must be increasing if the temperature is increasing. So I'm adding more energy to this system. So this allows the molecules to overcome those intermolecular forces. So when I'm adding energy, I'm kind of breaking those intermolecular forces between the particles, and because of that, they're able to flow more freely. They're able to move around as how they wish. So viscosity is dependent on three things. Remember, that would be, we said temperature, particle size, and shape. What was my third one? Intermolecular forces. So intermolecular forces, size and shape, and temperature. Okay, next characteristic of liquids is surface tension. Just go ahead and get all this up here. Okay, so surface tension is the energy that's required to increase the surface area of a liquid by a given amount. Now, intermolecular forces don't have an equal effect on all particles in a liquid. Imagine that you have like a glass of water. No ice, just a glass of water. The particles that are in the middle of this glass, the water particles that are in the middle of this liquid, they can be attracted to particles above or water particles below, or they could be attracted to water particles on the sides. So they can have an attraction from any direction. But if I think about the particles of water that are at the surface of that cup, there are no attractions from above to balance out all of the attractions from below. So I'm going to go ahead and skip to, I think I have a picture here. Yeah. Okay, so this would be a really good particle picture, particle diagram, which you've heard before. Here's what I see. Let's just say I have a flask of water here. Here's what I see in the middle. So I can have all of these water molecules can have attractions from above, from below, or from the sides. So they can be attracted in all of these different directions because there's water coming from every direction, or they're surrounded by all of these water molecules from all directions. But if I look at this one, if I look at what water is at the surface, then the molecules of water that are at the surface here, they have no attractions that are acting from above. So every attraction that they have could be from the sides or from down below. So because of this, surface tension, particles on the surface are typically pulled from below, but not from above. And this unbalanced force of having all of these water molecules at the surface being pulled down is what creates this surface tension. So if you don't like spiders, I'm really sorry. I'm not a huge fan of spiders either, but I think this is a really fantastic picture that shows this is the reason why spiders can walk on water like that, because there's so much surface tension where the water at the surface is being pulled from below. So it's almost like just stretching this piece of thin plastic over this sample of water, so you can just like walk right across it. And that's exactly what happens with a spider. Whenever you have water droplets on your car, so this is another example, I see that I have all of these water droplets in the middle that have interactions from all of the water molecules around them. But if I look at the ones on the outside, it's almost like they can create this nice little thin layer or surface tension, because all of those particles in the middle are trying to attract those ones from the top, pulling that attraction down further into that little water droplet. And that's what's creating that surface tension. So let me go back to our last slide. Okay, so surface tension is just a measure of this inwards pull by particles in the interior, in the inside of that liquid, or in the middle of that liquid. The stronger the attraction between particles, then the stronger the surface tension. So water is a fantastic example that you have really strong hydrogen bonds that are interacting between each water molecule, and so it's going to have, or it's going to exist, or exhibit a really strong surface tension. Now, sometimes surface tension, we don't want it. Sometimes it's really hard because if our clothes get dirty, it's really hard for us to get the dirt out of our clothes. It's also hard to maybe break sometimes that surface tension. So we've developed something called surfactants, and surfactants are compounds that can lower the surface tension of water. So surface tension is why water alone is not going to clean your clothes. We need soap, which a surfactant is just maybe a type of soap, or that's one example of a surfactant. We would need soap to break down those hydrogen bonds, so then that way the water can carry the dirt away. So soap, surfactants, soap is a surfactant. Surfactants are just breaking those hydrogen bonds, or in another case, maybe it's not a hydrogen bond, it could just be any type of intermolecular attraction. It's reducing those intermolecular attractions so that way water can take that dirt away. Okay, so two more factors or characteristics about liquids. We have cohesion, and cohesion is the force of attraction between identical molecules or intermolecular attractions. And adhesion is the force of attraction between molecules that are different. So I really like this picture here of adhesion and cohesion, because this is showing cohesion. I have two water molecules here, and I have cohesion between the two water molecules. They're identical, so they can have cohesion. Now, adhesion would be between the water molecule and then this glass container, or whatever other container that this is in. And I can say that I'd have adhesion here, I'd have it here, and then my cohesion would happen between the water molecules. Whenever we place a liquid in a test tube, or whenever we place a liquid in a beaker or a flask or anything, we see that there's that creation of the meniscus. And remember, that's that little concave curvature that we see in one of those types of glassware in chemistry. And that's because of adhesion. So it's an attraction between that liquid and then that glass container. So that's also what we're picturing up here. Okay, so to get into solids, now solids, we're going to kind of go through the solids pretty quickly. Solids contain particles with very strong attractive intermolecular forces. And these strong attractive intermolecular forces, this is what's limiting the motion of solid particles. So it's the attractive forces in solids that limits them from moving. Now, they are still moving because, remember, atoms still are always in motion. It's just that these particles are fixed in such a way that they're only able to vibrate in a very certain spot. So these atoms in a solid are able to vibrate, or molecules, particles in a solid, they're able to vibrate, so they're still moving, but they're in a fixed position. In general, we know that the particles in a solid are more closely packed than those in a liquid. So most solids, we would consider them to be more dense than most liquids. And when liquid and solid states coexist, so let's just say that I have ice and water, that could be an example, typically the solid almost always sinks into the liquid. But we have a very big exception there, and that is ice and water. So most solids are more dense than liquids, but we have that exception, which is water. Ice is less dense than liquid water. And the reason of that is because hydrogen bonding in ice will create this open symmetrical structure in this ice in our ice structure. So it's kind of creating this more empty and open space, which a solid really doesn't have that. They're very packed together in a very orderly way. So the hydrogen bonding in ice creates, again, like I said, this open symmetrical structure, and it keeps the water molecules in ice farther apart than what water is in a liquid state. So I gave you another particle diagram here because I think this one is fantastic. This would be the hydrogen bonds that are acting in the structure of ice. And then, of course, here I have my water molecules in just liquid form. So I have all of this open space here in ice because I'm creating like this open structural hydrogen bonding kind of structure. And in the other one, I don't have very much open space. Those water molecules are very close together, and they're able to kind of flow around. But the reason that ice can float on water is because of these open spaces here in ice. And this, again, is one of the rare examples that we have of a solid being able to float on that liquid. Okay, we've talked about this before, that solids, crystalline solids are just solids with atoms, ions, or molecules that are arranged in an orderly geometric shape. Now, to be more specific with what we had talked about last time, there are 3 different types of crystalline solids, which are shown here below. And what's different about each of these types is just the location of particles. And these location of particles are just represented as points, and it's just points in a framework. And we've also called crystalline solids, we've called these specific structures crystal lattices. So that shouldn't be anything new to you either. We've talked about that before. In letter A, this is called just a simple cubic cell. And in a simple cubic cell, the particles are only arranged at the corners of the cube. That's going to be different than B, which is called a body-centered cubic cell. On B, I see that I have atoms in the corners of the cell, but I'm also going to have a particle in the center of the cube. So simple cubic unit cell is just where I have particles in the corners of the cell. Body-centered cubic cell is where I have particles in the corners, and then one particle, or a particle in the center of the cube. On C, this one's called the face-centered cubic cell. And on the face-centered cubic cell, I have particles in all corners, but then I also have a particle that's in the center of each cubic face. So that means if I'm looking at this plane, I have a particle right here. If I'm looking at that plane or that part of the cube, I have a particle here. If I'm just looking at this one, I have a particle here. But if you would compare these two, this particle is right in the middle of the cube, and I don't have a particle that's right in the middle of this cube, okay? So those are your 3 different types of crystalline solids. Now, we have several different forms of crystalline solids. We could have an atomic crystalline solid, we could have a molecular crystalline solid, a covalent network for a crystalline solid, ionic or metallic. And this chart just goes in to describe the characteristics of each type. Also gives you examples of them. So for, let's just say, the one that, what I care about you knowing so much from this chart is just the characteristics of each type. So a molecular crystalline solid is fairly soft, it's a poor conductor, and then it has a pretty low to moderately high melting point. Versus a covalent network is very hard, very high melting points, and often have poor conductivity. Now the difference between molecular versus covalent network, because molecular compounds have covalent bonds, so what's the difference between those two? A covalent network is something that can form multiple covalent bonds, and they're pretty rare in terms of how many covalent networks I have, but very common example ones are with carbon and with silicon. And I'm going to show you the 3 covalent networks that carbon can make. These are the 3 covalent networks that carbon can make. This would be the structure for diamond. This would be the structure for graphite. And this is called a buckyball. Now, diamond, super strong, and it makes this covalent network. And all of these are just carbon atoms. And they make these really nice, very orderly, structured, different shapes, different geometric shapes. And that's what makes it so strong. Graphite here is still just all carbon, but the way that the graphite is bonded, the way that the carbon atoms are bonded to one another, makes it where it creates like sheets of carbon, which is why when you're writing on your pencil, with your pencil, the reason that you can get this nice, smooth, product from your pencil is because that pencil lead or graphite is coming out in just carbon sheets. So it's kind of cool. The last one here are buckyballs, and buckyballs are pretty new. They have been under a lot of research lately, especially in a cancer field, but it kind of looks like a soccer ball. So these are our 3 different types of covalent networks for carbon. So you can just see that there's multiple bonds, multiple covalent bonds, and that's just going to be a little bit different than our, than just our molecular crystalline solids. And ionic solids, we know are very hard, but they're brittle. Why are ionic solids brittle? Remember that if we took a hammer to an ionic solid, then I'm going to have a cation and maybe another cation come in contact with each other. And when 2 like charges come in contact, they repel, which is the reason why ionic compounds are so brittle. Because it's almost like I'm shifting the position of the cations and anions, and if I get the same charges next to one another, they're just going to move away. And then finally I have metallic solids, and we know that they're malleable and ductile. They could be soft to hard, low to high melting points. So probably what I would ask you is about covalent networks being very hard, having very high melting points, ionic networks, which are hard and brittle, and then metallic networks. I'll just probably ask you about the malleable and ductile, only because we've talked about that before. Okay, last one. On solids, we can also have a type of solid that's called amorphous solid. And the term amorphous comes from a Greek word that means without shape. So an amorphous solid are solids in which the particles are not arranged in a regular repeating pattern. So in our crystalline solid, we know that there's a definite pattern, a definite shape. And in an amorphous solid, there's not any regular repeating pattern. Now, amorphous solids can form when molten material cools very quickly. A really good example, or actually several examples of amorphous solids are glass. Glass is a good one. Another example is rubber. And then another example is plastic. So those are all different types of amorphous solids. Now, I'm going to continue with phase changes on Friday, so I will see you guys tomorrow. Bye!